বলো।
স্যার আমাকে জয়েন করার চেষ্টা করছি।
আমি এই জাস্ট ডেস্কে এলাম, আমি সবাইকে জয়েন করে দিচ্ছি করে। তোমরা আজকে কে কে এসেছিলে অফলাইন ল্যাব করতে? অনেকে?
আমাদের সেকশনের
কোন সেকশন বলছি? এনবি সেকশন? আমার দুটো মিটিং খোলা আছে তো, বুঝতে পারছি। এই সেকশন থেকে কজন এসেছিল? 20 তারিখ থেকে। আচ্ছা, তোমরা সে পিছিয়ে নিয়েছো। আচ্ছা আচ্ছা, এই সেকশন থেকে এসেছিল আজকে তাহলে। ওকে, গট ইট। আচ্ছা, বি সেকশনের মিটিং এ বেশ কয়েকজন পার্ট টাইম স্টুডেন্ট ঢুকবে, ওরা তোমার সাথে ক্লাস করবে আজকে। সেকশন এতে 64 স্টুডেন্টস। আরো আসবে নাকি? বাই দ্য ওয়ে, সেকশনের সিআর কি এখন?
হ্যালো স্যার।
রাইসা, তুমি সেকশনের সিআর?
হ্যাঁ স্যার, আমি আর সায়ন।
হ্যালো।
আচ্ছা, ঠিক আছে ঠিক আছে ঠিক আছে। তোমাদের সিআর অনেকবার পাল্টে গেছে। তোমরা সেকশনের কজন আসছো অফলাইন ল্যাব করতে? 15 জন মতো নাকি?
Yes.
So I guess we'll meet. I shall meet some of you, at least one group, maybe group 1 tomorrow in control lab. So I will be explaining this very lab in a physical mode. Let us see. সেকশনে ক্লাস কি শুরু করা যায়? আর একটু কেউ
হ্যাঁ স্যার।
আর কেউ
হ্যাঁ স্যার।
হ্যাঁ স্যার।
ওকে। সেকশনে আমার স্ক্রিন দেখা যাচ্ছে?
ইয়েস স্যার।
Yes, sir. Yes, sir.
ঠিক আছে।
ইয়েস স্যার।
আচ্ছা, এই ইয়েস স্যারটা না সেকশনে যে কোনো একজন বলো, না এতগুলো ইয়েস স্যার আসছে, মেবি তোমাদের সিআর সেই ইয়েস স্যার বললেই হবে। ঠিক আছে? হ্যাঁ, আমি যখন কোনো কোয়েশ্চেন করবো তখন সবাই আনসার করতে পারো। ওকে, থ্যাংক ইউ। So let the recording start, then I'll start the class. It's taking time to get recorded. Okay, so the topic of our discussion here is based on this laboratory experiment, that is a simulation of a second order dynamic system on analog simulator. So before I start the topic of today's laboratory experiment, I guess it is very much important that we recap what do you mean by analog simulation or an analog simulator. What is the very purpose of this analog simulator or analog simulation? This has been a part of your course in signals and systems in your second year, second semester course, but I'm not sure whether I've covered it properly or not. So I'll just give a brief overview to this situation or to the topic. Now, analog simulation is used to solve various types of problems. Now, what type of problem? A typical simulation consists of simulating a physical system, and this process involves a mathematical model of the system that consists of one or more differential equations and initial conditions on the variables of interest. Okay, in any case, you do not have to write your roll number for your attendance. I am using an attendance app so that your all your attendances will be registered. Okay, as soon as you log into the meeting, and it also registers the duration for which we're attending the class. So there's no need to write your roll numbers. Okay, the attendance is already been taken, and it will be taken throughout the class automatically by the app. Okay, so we have to physically represent. Represent a physical system, we have to use a mathematical model of the system that consists of one or more differential equation with initial condition on variables of interest. Now, the most general purpose of analog simulation employs active electric circuits. Why? Because these circuits have no moving part. And that means they have a very high speed of operation. They are very accurate, and they provide a very high degree of versatility. So active electrical network or circuit is normally used for analog simulation, and we'll follow that. Now, active electrical circuit basically consists of resistors, capacitors, and op-amps. And these are capable of simulating any linear system, specifically linear time invariant system. Okay, because the forward voltage transfer characteristics of these networks are analogous to the basic linear mathematical operations that we encounter in modeling of dynamic systems or the modeling of dynamics of any physical system. So the input-output voltage of an analog simulation based on this electrical active network will be analogous to the corresponding mathematical variables. They will be analogous, not the exact value. Any mechanical system, as you have already heard about the analogous systems, any mechanical systems can be represented by this electrical network, electrical active network, so that the only condition is that the dynamic equation governing them should be identical. They should be represented by an identical form of differential equation. The coefficients will be different, but the form of differential equation will be same. If so, then we call that class of systems consisting of electrical, mechanical, even hypothetical systems to be an analogous system because they carry the same dynamic equation. Now, but there is a limitation in this analog simulation. What is the limitation? This limitation is due to the limitations associated with the computer or equipments. Therefore, as we know, the analog simulation in active circuit we use op-amps, and op-amps are limited by their output voltage with respect to the bias voltages, and they are normally limited to a range, say plus minus 12 volts or plus minus 10 volts, which is the bias voltage for the op-amps. So whatever analog simulation you carry out, the output voltage of the op-amp, of any op-amp, should not exceed this range of value. So there's a certain restriction. Whenever you deal with such restrictions, what situation calls for is that to sustain a analog simulation within this allowable range of operation, you have to use what is called a magnitude scaling, so that the output of these op-amps they remain within the stipulated range without saturating or overloading the analog simulation components. So what are the normal simulating procedure for developing a simulation? First, you have to determine the mathematical model which describes the physical quantities of interest that you want to model or that you want to study. Then you have to develop an analog block diagram to relate the sequence of mathematical operations. I'll show you, give an example, I'll show you. So just read out the points first. And then you have to connect the electrical components accordingly to simulate or to emulate the block diagram in a physical mode. No, I'm not representing anything. I'm just talking. Okay, so when I present, I'll show you. So then, once you connect the electrical equipments accordingly, then you have to operate the simulation and observe or record the output or the concerned variable. Now, these variables or the output values will be in the range of the equipment or the simulator. That is from minus 10 volt to 10 volt, plus 10 volt. Then it will be your task to convert these variables to their proper physical form via some transformation. Okay, so what the analog simulation will give you a basic idea of how a system will behave under such conditions. Just a second. Okay, sorry. So, in order to, our objective will be to solve a given differential equation via this analog simulation. Now I am presenting a whiteboard. Can you see?
Yes, sir.
Okay. Now,
Yes,
since
sir.
our concern is linear I think this it doesn't require this much of writing. I think all of you know the linear time invariant system. That is the differential equation depicting the dynamic behavior will have constant coefficients. Okay, so in order to solve this differential equation corresponding to this linear time invariant system, what are the basic operations that we need to solve the differential equation? What are the basic operations that we will be reading? One will be summation or subtraction, whatever is it. Then sign inversion. This will be part of the subtraction. This summation with the sign inversion. Then multiplication by a constant. Finally, integration and so these are the five fundamental operations that we need to follow, the basic operations that are required for solving a differential equation, which will be carried out by the analog simulation. Among this, just to be noted here, from practical point of view, this integration is recommended or it's easier to implement and it is more preferable than this differentiation because the only reason is that the signals involved in analog simulation are all physical or real signals, say voltages, currents, etc. And therefore, the measurement of such signals are always corrupted by noise to a certain extent. And therefore, if you use a differentiation of these noise signals, which normally are of very high frequency term, a differential will yield a very large value of such signals. And that signals, those signals will then tend to dominate the actual signal or suppress the actual signal. That's why differentiation is not normally used. Whereas in integration, since this noise signals, normally they are kind of a sinusoidal signal with very low value of mean, or in other words, when passed through integrator, this integration will average out this noise. So the output of the integrator will be much precise as compared to the differentiation. Or you can say this noise will be averaged out by the integration, whereas by differentiation it will only accentuate it. So differentiation is not usually used for analog simulation. Only the first four stages are used. Now, How does this analog simulation work? For that, let us take an example. Suppose we have to solve a differential equation given as dy dt equal to y and boundary condition y0 equal to 1. I may have taught you in the theory class, but since it's long back, so I'll just give you the brief introduction, then I'll come back to the laboratory experiment. So integrating this, what do you get? You get yt as y0 plus so this is the solution. Now, how do we implement this in analog simulation? This can be implemented in an analog simulation block diagram like this. You put an integrator, and the input of the integrator, you incorporate this. If you have dy dt at its input, then what do you know? The output will be y. We know that. But given the system equation, we know this dy dt nothing but y. So what you can do? You can simply connect. And what about the initial condition? The initial condition should be fed directly like this. So in this situation, it is not necessary to know that what input is given to the integrator to solve the equation. But rather, it is necessary to ensure that the input to this integrator is actually the output at the same time, or the output should be fed back to the integrator to simulate this differential equation. Therefore, the basis of the analog simulation for solving a differential equation lies in the fact that you have to feed the unknown output back to the input to generate the solution. You do not have to bother about what value of input you need to feed to the integrator to obtain the output. Just you have to ensure that the proper circuitry is there so that it ensures that the differential or the input to the integrator is the proper variable that you are transmitting actually. If you can ensure that, then you can be rest assured that the output of the integrator will be the variable of interest, right? So this is how analog simulation works. You do not have to think about the value of a particular variable at each point of a simulation diagram. Rather, you can concentrate on making sure that the flow of signal is maintained in accordance with the differential equation. See, in this differential equation, it demands that this dy dt should be equal to y. And you know, if you integrate dy dt, you get y. So the only operation that you have to need is to ensure that the integrator input is fed from the output itself. So y is the integrator input to the integrator. And since there's an initial condition, we have to incorporate. This is the constant value is equal to 1 signal here. So this is the boundary condition for this solution to exist. बोलो अच्छा अच्छा हाँ yes thank you. So this is the basic essence of an analog simulation. Okay, now let us see how do we obtain the analog simulation following a systematic procedure. Say for the time being, we are given a differential equation and putting t in the parentheses to make sure that these are the variables. We have to solve this or obtain an analog simulation for this. Okay. So what we have to do, if we know that if the derivative of a particular variable is known, then it may be integrated to obtain the variable. In this context, if you say, you can see that if x double dot t is known, by an integration to yield x dot t, and by another integration it will yield xt. So this is the basic philosophy behind this analog simulation that will follow. So since each integration now results in one stage towards the final value, you can connect them in cascade like this. Okay. Now, given a second order differential equation that we have here, so what we have to do, we have to find out the highest order derivative term and express that in terms of the other derivative terms or the variable itself. So we have to only find out the expression for x double dot t as a function of x dot t, xt, and input if any. This is the primary term, primary work. If you can obtain this expression, then you can connect the suitable signal lines to simulate this equation. And from that, you can rest assured the following the two integrations, you will get the respective x dot and x, these two variables. Okay? This is a kind of a circular argument. Why? If you know xt, then you can calculate x dot t and from x dot t, x double dot t following a differentiation. But since this is not recommended, what we will do, we'll assume that x double dot t is known, and from that we'll calculate x dot t and xt. So it's a kind of a circular argument that we're having. So we'll follow this path rather. Okay. And next, this boundary value condition, the initial conditions are required because, in fact, a differential equation only represents the class of solutions. And this initial conditions, which are called the boundary value conditions on the specific variables of interest, will give you the particular solution. So one need to consider these initial conditions in deriving this analog simulation. Okay, so this is a very important part of this analog simulation, right? So let us now see. In the first step, we have to find out the expression for d2x dt square and assume that this is known to you. This expression is known. I'll draw it here. Okay, if we assume that d2x dt square is known, then what we can do, we can simply put x double dot, and if we put through an integrator, the representation of integrator, we'll get the minus n. Since the op-amp circuits that we're using will yield the integration with a negative sign. So we pass through another integrator, we'll get the x. So the first step, draw this. Now to obtain the expression for x double dot. How? Given the differential equation, you can simply write that x double dot is equal to basically 0.5 x dot minus x plus 4. So this is a driving equation. So if you want to calculate this x double dot, what I will do, I'll simply use a summer. Now this is again having an inverting gain. So what do I have to incorporate here? For 4, minus 4, for minus x, I have to incorporate x here and then 0.5 x dot. So this is stage 2. Now you have to now combine these two results together, right? You have to connect the dots now. So x should be connected to this signal, and what is the actual value? It's a, you can connect them straight away. So the first, this element is covered. Then 0.5 x dot, that means you have to get 0.5 x dot from here. Since it's minus x dot, what you have to do, you have to first convert it to x dot via an inverter, and then pass it through again. This is a value 5. Now this constitutes the analog simulation for this equation. It will give you the general solution. Now I have to incorporate the initial conditions. So for x dot, this should be initial condition. Since the output of the integrator is minus x dot. Now since this integrator itself contains all inverting operations, so it should be minus of this. Because you are solving for minus x dot, the initial condition should be of minus x dot 0. But this, since this is an inverter in the integrator inherently in its IC path, so it should be another minus over. So this is how the magnitude and the polarity of the signal should be determined. And similarly for this case, what is the output x? So it should be x0 initial condition and with a minus sign. So this is the analog simulation diagram of this. Now there is a problem with this simulation diagram, like how many connections? Okay, and this minus 4, how can you calculate this minus 4? You can simply write again, simply add a gain of 0.4 with a source of minus 10 volt. So we will get here minus 4. So you have determined all the 3 signals over here. They will be connected to this inverter with a gain 1, and these gains are all 1 for the time being. And what I have done, I have realized these signals physically. Minus 4, x can be fed back from here, and minus x dot, from minus x dot you can obtain this 0.5 x dot. So this is how this analog simulation for this differential equation can be obtained. The only problem is that, see, these integrators have multiple points. So it can perform the operation of both integration and summation simultaneously. All the integrators. I'll show you that. But if you use this formula, what will happen? There will be addition of these 3 connections, and this connection, and this another component necessary for this sort of connection. So what we will do, we will next try to eliminate this summer, so that the number of connections, the number of components becomes minimal. So if you eliminate this summer, what will happen? There is a minus 1 inherent here. So this minus 1 will have to be eliminated. And since this is a direct signal from here, passes to minus 1, so you have to incorporate a minus 1 over here. So ultimately, what will happen? And this minus 10 volt has to be changed to plus 10 volt. Because this inverter I am taking off the circuit. So everything has to be multiplied by minus 1 on each of the circuits. So what will be the final form? The final form will be something like this. This will be first integrated. And since we have mentioned that the initial condition x dot 0 is equal to 1 from this expression, you can write this to be so this is for the second integration, and x0 equal to 0. See, so this will be simply grounded. So this output will get x. Now, we simply connect 0.5 here. 1 is 1, so also 1. And this finally, for the inverter. So this will be the final analog simulation diagram for this differential equation. And what is the differential equation? X double dot plus 0.5 x dot plus x is equal to 5. 4 with x is 0 equal to 0 and x dot 0 equal to 1. So this is how another simulation for a second order differential equation can be obtained. So this is a very fundamental part, and we have to start from here. The problem next that I want to discuss here is a situation where the process of solving a particular differential equation yields an output from an amplifier which exceeds the range of operation of the amplifier. Okay, so or in some situations it simply exceeds the value of the amplifier range, and what happens, the amplifier output gets saturated and it doesn't show the actual nature of the response. And this is basically due to the equipment constraint which restricts the maximum voltage output for the amplifier, say to 10 volt. Therefore, this amplifier overload will occur when the problem dictates a large voltage output. This problem must be tackled by what is called magnitude scaling. Now, how to use the magnitude scaling? The magnitude scaling is used to fit the physical variables within the range of the component operation or operating range. Now, it would be necessary to scale up some part of a problem or to scale down some other parts. How? You may ask that you have been so far talking about the exceeding value exceeding the range of the amplifier. Obviously, this need to be scaled down. So then, why are you talking about the scaling up? Let me give you an example. Suppose your problem at hand is to calculate the speed of a rocket. Okay, and if you choose to relate that 1 volt on your simulation is equivalent to 1 feet per second in real problem, then it will be impossible because the velocity will be very, very fast. So what you have to do, we have to choose a scale such that instead of 1 feet per second, if you choose 1 mile per second equivalent to 1 volt, then you might be able to restrict the velocity or the representation of the velocity within the range of operating range of the component. So you have to scale the scale down, because in the previous case we have been considering 1 feet per second equal to 1 volt. So for anything we would say 40 miles per second, it could have given a very, very large value. Okay, so there have been thousands of feet or thousands of volts were required. So if I use this, so still it will be like 40 volt. Maybe the range is again exceeded. So I may have to use 10 miles per second. So it will be within 4 volt. So this is how we can scale the physical quantity based on the value, actual value of the physical quantity. So before starting the analog simulation, it is very important that you estimate the maximum value of the physical quantity that you want to manipulate or simulate. Sorry. Now, in the same problem, suppose you're using this scale to measure the speed. Suppose in the same problem, you also want to measure the acceleration. And this acceleration is normally in the range of feet per second square, which is on the basis, if you use the acceleration which varies in the range of feet per second square. Now, if you use this scale of 10 mile per second square, then the value for each unit of acceleration that you will get is something like this. For each unit of physical acceleration, the voltage deviation in computer level or the equipment level will be this. See, this voltage is very, very, very small, and it is at the level of noise. So what I have to do, if you use the same scale for the velocity and for this acceleration, you'll be in big trouble because the acceleration may never be detected. And even if you detect the acceleration, you cannot separate it from the noise signal. So what I have to do? We have to use a different scale for the acceleration. Maybe for acceleration, you use the feet per second square scale. So there is never in such situations there will be never an uniformity between the scaling. And we'll see an example where you have to use different scales to represent different variables. Now we've been talking about the magnitude scaling. Let us take a physical example, or not physical, a mathematical example where the scaling will be necessary. Suppose you have to solve a differential equation given by x dot with initial condition given as 0. So if you solve this, can anyone tell me what is the solution of xt? Okay, so this will be the solution of this differential equation. If we plot the response, and if this is say 20, the response will be something like this. Whereas the value is the actual response, but this is a 10-volt scale. So what will happen to the actual response, actual output that the op-amp will show is that it will reach a, that will saturate. It will not show the actual response. So what we have to do, we have to magnitude scale this particular equation so that we can represent this within this range of 0 to 10 volt. Now how that can be done? Because in this case, clearly the amplifier overloads and it cannot supply this 20 volt because this range is up to 10 volts suppose. So to avoid this difficulty, we have to use a different correspondence between the problem variable and the computer variable. What is the problem variable here? Xt, and the computer variable is Vt. Now how, which sort of a um, association or correspondence we are looking for? Actually, we are looking for we have seen that x max is 20 volt, and what is the range of operation for the voltage that we have? Vmax 10 volt. So what we will do? We'll define the computer variable Vt as xt by 2. So what will be the value of Vt max? 10 volts. So it will remain within the range of operation. So given this, how we can represent this equation? See, from this expression, what you can do, we have x dot plus 0.1x equal to 2. This we can represent as 2 into x dot by 2 plus 2 into, sorry, huh. So from this, you can simply write the modified equation as this x dot by 2 is basically v dot, and this is v, and this 2 you can take common and write over there. So this will be the modified equation, right? So what is the solution? The solution will be the response will be something like this. So it will show the actual response within the scale of say 0 to 10 volt, that is without overloading the amplifier. So this is how the magnitude scaling basically acts. So what you have to do, the basic idea is that the analog simulation does not solve the actual equation, but an analogous equation. And the analog voltage is normalized to units. Now, it is common practice to redefine the magnitude of the reference voltage and all associated input and output voltage on an analog computer in terms of what is called an analog unit. This VT is represented as analog unit. Okay. Now, by definition, the maximum voltage obtainable on the computer is plus 10 volt. So, one analog unit will be plus 10 volts. Therefore, the scaling problem in terms of these units makes a scaled analog diagram which is machine independent, just like your per unit system. You represent the equation in a per unit system. So, whatever limit you have 10 volt, 15 volt, if you can represent them in terms of a per unit system or in the percentage of scale, full scale range, then it becomes very easy and it becomes independent of the machine that you are dealing with. Right? So, given this, we'll now see how to formulate this problem now. So given our differential equation at hand, x dot t plus 0.1x t is equal to 5 with x0 equal to 0. This is the equation that we have. And now we see that the maximum value is 50. And what is the allowable range of value? Say 10 volt. So what we'll do, we'll define the computer variable x is a physical variable, and this computer variable vx, sorry, is equal to lx into x. Now, what is this lx? Lx is termed as level of x. So, for this, how it is calculated? 10 by x max. So, it will be 10 by 50, that is 1 by 5. So, what will be the vx? The computer variable vx will be x by 5. For this case, it will, oh, it was like 2, na? Sorry, not 5, it was 2. Half x by 2. Now, following this, we make a table that the problem variable x estimated maximum x max is 50. Uh, level of x, that is lx, or maximum not 50 again, it's only 20. Half. So your computer variable vx will be x by 2 and initial condition x0 equal to 0, and following the same vx0 equal to 0. So this is the data that you need to obtain the simulation, and from that We've seen that the corresponding equation that we'll get is v dot plus 0.1v is equal to 1. Or you can simply write v dot is equal to 0.1v minus plus 1. So this is the differential equation that we have. So what is the simulation diagram? We will draw the corresponding simulation diagram. Single integrator. X0 is 0, so it will be grounded. So this will be your x by 2. Sorry. By 2. And 0.1 with minus 10 volt to represent this one. And we'll have to represent this minus 0.1v 0.1. So this is the analog simulation for this, and the response, corresponding response, you'll see that. And write very slowly because I've already drawn it. It is something like 10. This is Vt, and this is T. Yes. Okay, so this clearly depicts the entire dynamics within the stipulated range of operations. So this is how you can systematically obtain the analog simulation of a first order system. Now what I'll do, I'll next explain the analog simulation for a second order system, and I'll leave the problem for you to formulate the same for the given problem on your problem sheet. So let us see. I'll go through it very quickly. So given the equation x double dot plus 2x dot equal to 0 with initial condition x0 equal to 20, x dot 0 equal to 0. This is the initial condition, and more importantly, it is given that the maximum value of x is 20 and that of x dot is 100. So you have to find out the corresponding analog simulation. First stage, write down the equation. Right. Next, find out the levels. About Lx 10 by 20 and Lx dot. What about this? 10 by 100, 1 by 10. So fine. So from this, write down this equation in terms of this expression. So we can write minus x dot contains. So what we have, you vx x2 and vx dot x by 10. So I have to write this x dot by 10. So I have to write this as minus 2 into 10. Write this minus 25 into 2. So this is the scenario. What are the initial condition? Vx0 will be 10. Vx dot 0 will be 0. So this is the initial condition that you get. Now, so you have to now simulate this via analog simulation. So let's find, we know that what we have to do. Yes. So from definition, this should be x by 2. And this should be x dot by 10. But interestingly, the output of this integrator 1 is minus x dot by 10. So what should be the integrator input to the integrator? It should be minus, not sorry, right? So this should be the input. So instead of x double dot, what we have to find is the expression for x double dot by 10. So if you find that, you find that x double dot by 10, which will be the input to the. Have you understood that? To obtain this as an output of this integrator, the input should be x double dot by 10, not x double dot. If you put x double dot, it will get x dot minus x dot, but you're getting minus x dot by 10. So this should be the input. So how to obtain this expression from this expression? Divide by 10. So it will be like I'm writing this minus 5, this one first. Into x by 2 minus 2 x dot by 10. So this is the final equation. Right? Now we have to simulate this. So how to obtain this from this equation? See what you can do directly, just keeping in mind that this minus n is already taken care of. So it will be simply and since in the last lab we have seen that these pods cannot exceed the value of 1, so you have to use again 10 over here, and with 0.2 in 10 you get this 2. Similarly for the next phase you use again 10 over here because 5 is there. Zero 0.5 with 10. What are the initial condition? This should be 0 and this should be minus 10 volt. There's no need for input. But still, it is not complete. Because see, to get x by 2 at the output, this should be minus x dot by 2. But what we have here is basically minus x dot by 10. So there should be a gain equivalent to 5 over here. What I'll do, I'll multiply by 0.5 and 10. So this will be the complete magnitude scaled simulation, analog simulation for this differential equation given these conditions. The two things to be noted, this gain, just to take care of this situation that to get x by 2 at the output, you should get minus x dot by 2 at the input of this integrator. So to get minus x dot 2 from minus x dot by 10, you have to multiply by 5. So that I have done by this. Right? This is the analog simulation magnitude scale for this particular example. So this is what I have to discuss about the theory. Now, the experimental part will be very brief because I guess I have already discussed in details about the analog simulation and the methods thereof. So I'll just go through them very quickly. Okay, let me go through that. So first, let me show you the analog setup. The setup. Just to remind you, your memory is bad. So this is a setup that we have where these are the pods. These are basically potential dividers where you put an input over here of say plus 10 or minus 10 volt, and the output will be given by alpha V, where the alpha varies between 0 and 1. By this rotating this disk, you can vary the alpha between any value between 0 and 1. These are the ports. Now, see, there is no calibration on the port. I'll just go through briefly and very quickly. So, how do you calibrate these things and how do you set a particular value of alpha over there? That is being done by using what is called a port set mechanism. I think I have a better picture of port set mechanism rather. Okay, so this is the entire port set mechanism that I'm dealing with. What I have to do, you incorporate input a 10 volt to the input side of the port, say plus 10 volt, and the output side is then connected to this terminal. It comes from say port 1. And suppose you want to set 0.5 on the port, so there's a vernier scale. So you have to set the vernier scale at 500. You know that because it has a scale range from 0 to 1000. So the precision is 0.001. So if you set it at 500, you'll get exactly the 0.5 because 500 by 1000 is 0.5. So set this value at 500. And now there's a switch over here. If you toggle this switch to this side, whatever value you put over here, that will be shown in the meter. But if you toggle the switch to this side, then what it will do, it will compare this value with the output of this port. And since this is a reference port, we know if you set it at 500, the 0.5 will be the gain of the port. So the output with respect to a 10 volt, which is already connected internally to this and also connected to this port 1 externally. So the output of this port will be exactly 5 volt. And now we'll adjust the port 1 accordingly until these two voltages, this 5 volt and this also becomes 5 volt. Now how this difference is maintained? Once this is set in the port set mode, this meter only shows the differential voltage between them. And this red and green lamp indicate the polarity. Red lamp indicates, the green lamp indicates a negative polarity, whereas the red one indicates a positive polarity. If the green lamp is glowing, that means you have to increase the port setting. And if the red lamp starts to glow, it means you have to decrease the port setting of the port by rotating it counterclockwise. So the null position will be obtained, or the accurate position of the port will be obtained when neither of the lights will be glowing. So that is how you can set particular coefficient to the port. In case I have a video for that. Say I've connected a 10 volt supply to the port and the return path is from this to this. Now the green light is glowing. So I'm increasing the port by rotating the clock on side. Now red light has started to glow. So it has exceeded. So I have to fine adjust this port so that neither of them is glowing. A point will achieve. Okay, see there is no one is glowing and the deflection is minimum. So it has been set. Now if you change over to meter volt, it shows around 5 volt. So the port is actually set at 0.5. So this is how you can actually set the port at any given value. And these ports actually represent the coefficients of the differential equation, right? Because in the analog simulation, what I have seen, this coefficients, they are basically the ports where you input signal is coming over and output signal is coming over, getting from there. Now the input signal, you do not have to worry about the input signal. What you have to make sure is that this order of signaling is maintained. They have not maintained any fixed signal, only for the initial conditions. Rest, it's a sequence of operation. The signal coming from here out of the integrator, passing through this gain, whatever value it comes over here. So this sequence of operation will yield the final form of the response that we intend. Right? I'll just show you the how the pot set is actually obtained. See, now it's growing, so I have to reduce it. Now this is the null condition. Since it's a very delicate thing, it's very difficult to obtain the null. It's now 5 volt. So I guess I'll pause it here. So next, what you will do, suppose the pot is set and you obtained the corresponding analog simulation diagram following a particular operand problem. So let's look at the problem that we have here. The problem is that given a second order system like this, the values are given j and k, and f is suppose a variable value. The units are given. The initial conditions are all zero. So this is a standard second order differential equation. But the condition that is given is that the maximum value of theta 0 is 2, d theta d0, d theta dt is also 2, and this is also 2. This means whenever we're applying a step voltage of 10 volt, since we have only 10 volt source, the output will reach 20 volt at peak for theta 0, 20 volt at peak for theta 0 dot. So it will certainly exceed the range of the scale. So what you have to do, you have to scale down by choosing a proper computer variable. So if you look at the problem solution of the problem, you find that the proper computer variable corresponding to this situation will be something like this. See, this is the problem that we have. So this is all 2. We have to make them all 1. So they divide by 2. So j, this is the variables, computer variables. This is redundant though. So these two are important. So the computer variable x double dot x dot and x will be something like this. And this 2 will come over here. So this gain, theta is the input. This is the input. So this gain will actually manipulate the input gain. So the final simulation equation will be something like this. See, it was like k theta I, now it has become k by 2 theta I. So what will happen? This is the final simulation diagram following this summation part. You can now omit the summation part, then this will be omitted. Now this is how this magnitude scaled simulation can be obtained. See, this input side has a gain k by 2j. But previously, without magnitude scaling, it would have been k by j. So this half that is coming up, which will ensure that the input value is now filtered to 5 volt. So that will yield an output which is 2 into 5, that is 10 volt at max. That's how the output response will be restricted within the range of the amplifier operating value. The corresponding responses for 3 typical cases, like for underdamped case, it will be like this. The steady state value will be something like 5. For critically damped case, it will reach the value of 5. And for undamped case, it will oscillate between 0 to 10. And this is the max value of theta that we have. Now, how to simulate this? Now, this will be your task given the values of these parameters. You have the only option of changing the value of f. So you have to change the value of f to obtain. Now, what is the value of undamped f to obtain an undamped response? What should be the value of f? Anybody? To get an undamped response, it should be 0. The first case. Second, say underdamped, you can take any value. Say this 1.25. And then you have to find out the value for critically damped case. This I'll not calculate. You have to find out the value of critically damped case and simulate the same on an analog simulator following the circuit diagram or the connection diagram which follows from this somewhat from this figure. Obviously, this to be further reduced. I have not reduced it intentionally. So you have to further reduce this to a simplified form by eliminating this summer. Now, once you simulate that, how the responses will look, I'll show you the responses on it. So this is an say undamped situation. Let's look at the responses over here. I'm not yet started the simulation. What I'll do, I'll start the simulation by yes, I've operated it. Now see the value is the underdamped response. This indicates the input value. This is the output value. So the steady state value is almost half that of the input value. So it reaches almost the steady state. If we just take a look at it again, we get back to it. So the second time for underdamped response. See, I'm just starting the simulation. No, this is the input, this is the output. So look at this value only. Set and then start the simulation. So it reaches a value of 5.92, then gets down, peak overshoot, there's the undershoot, and there's a steady state value around 4.77. So this is the underdamped response. Underdamped response. So next we will see what is called a critically damped response. I have tuned the F to yield the critically damped response. You have to find out the value of F. This will be your assignment. And once I operate that, I set and then I operate it. You'll see it reaches the value steadily without any overshoot. This is basically a critically damped situation, right? I wish I can show you the again video. As soon as start it, it moves very slowly to the final value. There's no overshoot whatsoever. That's a critically damped response. Okay, the undamped response is not opening. Let me just refresh that. Okay. One second. This video I've edited, but since it's not being edited properly, see, it's not opening. So for undamped case, what you see, just you have to adjust to the video. See, the undamped oscillation means 0 to 9.5 or 9.6 is oscillating like a sinusoidal waveform. This is because it's undamped. F is made equal to 0. But still, it's not reaching the value of 20. It's within the value of 10 because we have used a magnitude scaling operation. Right. So this concludes the session or the lab portion. Since it's very difficult to explain everything on this online platform, so I have mainly focused on the theory part and why this magnitude scaling is required. And I've given a couple of examples of this magnitude scaling simulation, how to obtain the simulation diagram. And finally, I have given you the task of obtaining this F variable to obtain the undamped and critically damped condition. And the underdamped condition can be followed from this. And given the underdamped condition, if possible, I will give you some data so that you can calculate some results following this plot. Okay, so I'll give you some data to calculate the value of zeta from this plot. So you don't have to use this plot. I'll give you some data for that. Okay, maybe following tomorrow's offline class, I'll give you some data to your friends, which they will share to you. And based on the data, you have to calculate the zeta value experimentally, and the theoretical value can be calculated by following the standard formula of second order system, a second order differential equation. And you have to tally them, you have to compare them. Okay, and you have to find out the value of f to yield the critically damped response. And during the response, corresponding responses, I've shown you the responses. I couldn't show the circuit diagram because it's very, very complicated. But the philosophy is like this. Okay, you have to connect from input side. I think it's a bit easy. So from input side, you have to connect. There's no input side though in this case. So let's go to this. From input side, 10 volt to connect to a port, 0.4. Then from the output of the port, connect to the integrator to the gain 1 port. From the output of the integrator, connect to the next integrator to gain 1 port. And from the output of the integrator, you get it back via an inverter to the second input of the first integrator. And then for the second output of the first integrator, get it back through a particular gain through the third input port of the first integrator. And also connect the port and the voltages according to the initial conditions. And once you simulate that, you just turn on the switch, a 10 volt step will appear because this 10 volt will appear suddenly. So it will be like a step voltage. So what you'll get at the output is basically this xt will directly give you a step response, which was obviously conveyed by the movement of the needle of the analog multimeter, analog meter that you had installed, right? So if we just look at the, I'll just repeat the experiment. Just look at the needle. It clearly indicates the value. If you can pause the simulation, you can see the respective values. As soon as you put the operate value, the 10 volt will appear as a step to the input. This is the first peak, 5.92, and first undershoot, 4.5, and then it will reach the steady state value of 4.77. Then a slight overshoot of 4.8. This is how you can obtain these peak points. And the first overshoot is very important. If you can have a time clock stopwatch to measure this time, you can also have MP and TP, and that will give you the idea about the zeta and omega n of the system. So you can calculate the differential equation from that itself, right? So this will be the task that you don't have to calculate that. You have to find out the value of f so that you get the desired 3 types of responses. So I guess I will stop here now. Now, do you have any? If you have any query, you can ask me. Any doubt? Anybody? And those who will be visiting the lab tomorrow, I'll explain whatever doubt you have. But those who cannot, I'll ask you to, if you have any doubt, you can share now. আর কোনো ডাউট আছে কিছু বুঝতে অসুবিধা হচ্ছে কোনো জায়গায়? দেখো আমি আজকে থিওরিটা বেশি পড়িয়েছি, মানে এক্সপেরিমেন্টাল পার্টে কানেকশনটা এতটাই কমপ্লিকেটেড, আমি ছবি থাকলে দেখাতে পারি কিন্তু তোমরা কিছুই বুঝতে পারবে না। এটা একটা কানেকশন ডায়াগ্রাম, এটা কিছু এক্সপ্লেন করা সম্ভবই না, তাই না? ইটস ভেরি ডিফিকাল্ট। So what I can do, I can at least চান্স নিতে পারি, বলে দিচ্ছি একটা ছোট্ট করে। Okay, I'll just give you a brief overview. See, I'll take a signal from this plus 10 volt and connect it to the input port. From that to the input of integrator, output of the integrator is connected to this, and this will come to the meter. This is a simple single flow line. Now for the feedback parts, I'll take this output and connect to the corresponding port. The output of the port fed here. And for the second feedback path, I'll take this output, connect to a particular port. The output of the port will be taken over here. Okay, in this case, you might ask that okay, it should be connected to an inverter. Okay, I'll connect it to the inverter. And the output of the inverter will come to this. This is the fundamental connection diagram. I guess I can give you only this sort of idea. And finally, this. Okay, green should be taken from here. This is the second integrator. And I'm connecting an analog meter over here. So a multimeter over here to measure the values. Right. So if I again show you the connection, you can see if possible. I'll try and show you the connection of the yellow lines. So from 10 volt, I'm connecting this to the input of a port. And from that input of a port, I'm connecting to this input of an integrator. This integrator is connected to the next integrator. And this goes to the output meter. Now for the internal circuits, what I have, output of the first integrator is fed to a port, and this output is fed to this. And output of the second integrator is again fed to the port. This output is fed to inverter, and the output of the inverter is then fed to the third point over here. So this is the fundamental connection diagram. For the second order simulation that we have been dealing with, like this. Now I have to also connect these initial conditions. I'm not connecting them. Right? So I guess I have given you some idea about the connections. Then once we put on the switch, turn on the switch, and put this operation like hold a set, the initial condition will be initiated, then we'll operate it, and we'll see the response over here in this meter. Okay. So that's it. So that's as far I can go with this mode. Okay. The rest I can explain for those who will be coming to the lab, and those who will not be coming to the lab tomorrow, please ask if you have any doubt. Otherwise, I'll stop the class. Okay, I guess I do not have any queries. You don't have any queries. So I'll stop the class now. Any feedback from your side? I'm otherwise.
স্যার ল্যাব রিপোর্টটা কবে সাবমিট করতে হবে?
আচ্ছা, ল্যাব রিপোর্টের ব্যাপারে আমি কালকে আর ফিজিক্যালি করুক, আমি তোমাদের বন্ধুদের কিছু ডেটা দিয়ে দেবো, তার উপর বেসিস করে তোমাদের রিপোর্টটা লিখতে হবে। ওকে
স্যার এক্সামও তো এসে পড়েছে।
পরীক্ষার পরে দেবে।
ওকে স্যার,
ঠিক আছে, একদম সব রিপোর্ট পরীক্ষার পরে, কোনো অসুবিধা নেই। ঠিক আছে। Okay, so you may leave now. The class is over. Thank you. Okay. Good night.
Yes, sir.
Good night.
Good night, sir.
Good night.